Today we are going to start a new chapter and a very important chapter so far as the ceramic materials are concerned. This is on electrical conduction in ceramics. Earlier we have mentioned that ceramics as a group has a very wide spectrum of electrical properties, and therefore, not only want to discuss those properties, but at the same time we like to understand what is how the phenomena can be explained in not only in different kind of oxides or different kind of ceramics, but in different materials as such, starting from metals to oxides to other compounds. So, our topic today is electrical conduction in ceramics, but initially we will discuss about the theories of electrical conduction or electrical phenomena as such in metals, semiconductors, and finally we come to ceramics. As you know, some of the ceramics are actually semiconductors, others are insulators, and many of them also have a metallic or superconducting properties. So, it is necessary for us to understand what is the basic phenomena involved in electrical conduction or how the materials respond to an external electric field. So, that is the topic, electrical conduction in ceramics, and the very first thing we like to discuss is the basic phenomena, the phenomena of electrical conduction as such. I think it is a very basic property of the material, many materials, and we just say that electrical conduction is the result of charge transport through a medium, either solid, liquid or gas, but our concern is primarily on solid today. Two basic parameters which characterize this particular transport phenomena, the charge transport phenomena, is the quantity of the charge which is getting transported and the velocity with which it is moving. So, q and Vd, Vd is the velocity, q is the charge. The conduction is normally induced by an external applied electric field. So, obviously, it is the response of the material to the external applied electric field, that is the property of electrical conduction, and what happens when this field is applied. To continue with that, according to Ohm's law, which is a basic law governing the electrical phenomena, the flux density, or in other words the current density J, is proportional to the applied electric field, and the proportionality constant is termed as the electrical conductivity sigma. So, we can simply write very simple equation J equal to sigma into E. So, sigma is the electrical conductivity, and as you know, the inverse of this 1 by sigma is rho, the electrical resistivity. So, we will be using these two terms very often, either in terms of conductivity or the inverse of that is the resistivity. Let us go a little atomistic nature or the microscopic nature of this particular phenomena. If we assume that Z is the number of electronic charge, that is E, with each of the mobile species, we are considering that there is a charge carrying species which is moving under the application of the external field, and it need not be an electron, it may be something else also, some other species, we will come to that in a minute. So, although electron has only one electronic charge, so Z equal to 1, but there may be other species in which the Z may not be 1. So, to generalize, Z is the number of the electronic charge E with each of the mobile species, and n is the number of charge carrier per unit volume. That means, it is the concentration, it is the concentration of the charge carriers per unit volume, the number per unit volume. The current flowing per unit cross section of the solid, that is the current density J, may be expressed as J equal to N Z E V D. Once again the velocity comes in and the concentration, and J D is the charge, total charge per species, and N is the concentration of that particular species. So, the total flux density or the current density in this case per unit area is equal to N Z E V D. V D is the velocity with which it is moving when you apply an electric field. V D is known sometimes known as the drift velocity, which is the net velocity of the charge species in the direction of the applied field or in the reverse direction depending on the charge, either it is negative or the positive. If it is negative, it will move in the reverse direction, if the positive in the same direction. Under certain conditions, it is also the average drift velocity between two consecutive collisions. If we assume that there are certain collisions taking place, again that phenomena I will be discussing in a few minutes. If there are number of collisions during the movement of the charge species with some obstacle, some barrier, the electronic charge with some barrier and obstacle, some coming in the way of the movement of the species, that is what we are talking about, the collision. It is colliding with some other barrier or obstacles during its movement, then the drift velocity is the average velocity between the two consecutive collisions. Applying Ohm's law, once again, sigma into E, that is nothing but J. So, N Z E V D. So, sigma equal to N Z E multiplied by V D over E. So, V D by over E we separate out, N Z E remains another component of this expression, and so you write N Z E mu. Mu is defined as the V D by E. So, V D by E is the another term we have introduced, is the mobility. We call it mobility, and this is the velocity per unit electric field. So, that is the definition of mobility, and we will come across this particular term mobility very often in our expression of conductivity. Now, we have introduced few parameters, and let us like to have the idea of the units. E, the electric field, it is volt per centimeter. J, it can be written as small j also, here it is written capital J, but it is same thing. Ampere per centimeter square. Number, that is the actually N is the concentration. So, the number per centimeter cube, that is or meter cube in different systems. Z is the number, it is only the integer, total number of electrons. It may be small numbers obviously, because there may be small electronic charges, either 1, 2, 3, 4 like that. E is the electronic charge, and which is a constant, 1.602 into 10 to the power minus 19 coulombs. Mu, an important parameter for conductivity of many solids or charge carriers, basically the mobility of the charge carriers, centimeter square per volt second, and sigma the conductivity, ohm inverse, centimeter inverse, or Siemens meter inverse. Okay. So, ohm inverse becomes actually Siemens, and if you talk about resistivity, the inverse of which is not listed here, resistivity, that is 1 over sigma, that is rho. Rho is ohm centimeter or ohm meter. We also like to introduce another very important parameter which is very relevant for ceramics or ionic solids. Particularly in ceramics, there may be more than one type of mobile charge species which may contribute to the transport process. Basically, we are talking about a movement of charge in different forms, and there may be more than one charge carrier, and in which case the movement of the charge actually give rise to the current. So, that is the as per definition. So, if there are more than one charge carriers, all of them will contribute to the current, or they will carry part of the current, total current, and they will correspondingly give rise to certain conductivities. So, the general expression of sigma t then, T stands for total, the overall conductivity is actually the summation of different conductivities arising from different species. The ith species, I varies from 1 to n. So, it becomes sigma 1 plus sigma 2 plus sigma 3 up to sigma n. So, in that context, a transference number refers to the fraction of total current carried by the specific charge carrier I by the total current, or the fraction of the total current which is being carried by that particular species, that is ith species. So, that fraction, that is T I, the transference number, equal to sigma I by sigma t, that is sigma I is the current carried by the, or the fraction of the current carried by the ith species out of the total current I t, or in this case if you write in form of conductivity, it becomes sigma I by sigma t. So, it is basically a ratio, or sometimes expressed in percentage also. Ceramic materials ideally may have 4 different kinds of charge carriers normally, that is the most probable type, or one can have, because it has electrons. Obviously, the free electrons will be there, some form of free electrons, may not be completely free, but it may be polar ions and so on, we will come to that later. It may be cations, it may be anions, and whenever there is a free electron, there may be a possibility of holes as well, the absence of electron or the vacancy of an electron. Or so, the concept of hole is also there. It is very similar to the vacancy, the concept of vacancy in point defects. So, there are in general 4 types of charge carriers one can anticipate, and these are free electron, free hole, cation and anion. So, particularly in ionic solids or ceramics in general, T, the total T is T 1 plus T 2 plus T 3 plus T 4, which will be equal to 1, okay, provided there are only 4 charge carriers. So, this will be very important when we will be talking about the ionic conductivity. In some of the solids, some of the ceramic materials are known for their high ionic conductivity, in which electronic conduction is negligible. It is either cation or the anion is the primary charge carrying species, and there one has to understand, and particularly when we will take it up some of the applications, the transference numbers becomes quite important. Now, these are some sub classifications of the whole gamut of different materials. There are 4 varieties of materials based on the electrical resistivity or electrical parameter or the electrical conductivity. I am sure everybody knows about that, but just for completeness, sake of completeness, we once again repeat it. It is superconductors, which is supposed to be the highest conducting materials available. In fact, they are supposed to have zero resistance. So, theoretically they will have a infinite conductivity. There are elements and also some ceramics. Okay. Also some ceramics are known for their superconducting property, particularly at a relatively low temperature. In fact, superconductors are supposed to be high TC superconductors, that means high temperature superconductors compared to many of the metals and alloys which has been listed here. Mercury, lead, niobium, tin, and then YbCO, it is actually a complex oxide of yttrium, barium, copper. So, YbCO, that is how the name came, and this is BsCCO, bismuth, strontium, calcium, copper oxide. So, there are very complex oxides. We look into it at a later stage. What are those materials, what are their structures, and why they are conducting, superconducting. So, this is a very specific group of material which are called superconductors, having the highest possible conductivity or near zero resistivity. For all practical purpose, resistance is 0. Then in the scale of higher resistivity comes the conductors. The resistivity is of the order of 10 to the minus 9 to 10 to the minus 4 ohm meters, and most of the metals are good conductors. That does not mean that they are all superconductors, but most of the metals are really good conductors and they fall in this particular resistivity range. Examples are obviously copper, gold, silver, aluminum, iron, nickel, and so on. Then comes the semiconductors. The resistivity is still higher. This is in the order of 10 to the minus 3 to 10 to the plus 3 ohm meter, and there are a very important group of materials. Some of their elements, some of their compounds, some of their oxides, and there are whole range of materials available under this semiconductor group. Of course, the semiconductivity was originally discovered primarily in silicon and germanium, and as you possibly aware that silicon is one of the most important material today for the microelectronics industry. So, it is the advancement in microelectronics actually came up with the development, with the discovery of silicon as a semiconducting material, and there are very important properties which is utilized in the technological area. So, without silicon we cannot think of a microelectronics industry today, computer industry, controlling telecommunication and everything. Then the highest range of resistivity, those are called insulators. The resistivity range varies between 10 to the power 5 to 10 to the power 17, is once again a very wide range of resistance. It is almost 12 orders of magnitude resistance. All these materials fall in this category and they have different exact values of resistance, but the important materials which are known to be good insulators, many of them are actually ceramics. The first thing comes porcelain. You know, porcelain has been used as an insulator in electrical industry or electrical power industry for a long time, because they have a good insulating material and it insulates one conductor from the other. Mica, window glass, PVC, polymer, Teflon is also another polymer, bakelite, diamond, and high purity silica. All of them have very good electrical resistivity, very high electrical resistivity, and a good insulating property. So, they have been categorized as insulators. So, we have 4 major categories under which all these different materials can be classified, starting from 0 resistance to very high resistance. This is just to give you an idea of the resistance values of some of the materials which we have mentioned just now. Silver is one of the very good conductors, one of the best conductors available, next to gold maybe. Silver is better, possibly silver is better than gold, but they are more or less comparable. 1.59 in 10 to the power minus 8 ohm meter. Copper next is about 1.68 into the minus 8 ohm meter. It is very close, but slightly higher resistivity. Pure germanium, which is a semiconductor. Incidentally, silver and copper are conductors. Pure germanium is 0.5 ohm meter, and pure silicon is a little higher, 2300 ohm meter. Silicon carbide is a ceramics, but a good high temperature semiconductor. These days silicon carbide is one of the useful materials for the ceramic industry, for certain applications of course. It is about 10 to the power 3, that means 1000. Glass, normal glass is an insulator, 10 to the power 10 to 10 to the power 14 ohm meter. Diamond 10 to the power 14 or more, and steatite porcelain, basically steatite is magnesium silicate. So, it is magnesium silicate porcelain, which is more than 10 to the power 17 ohm meter. So, once again we have conductors, semiconductors and insulators here. Well, having understood that there are a huge range of conductivities available in different materials, different groups of materials, their bondings are different, chemical bonds, nature of chemical bonds are different, and but so far as the resistivity is concerned, they can fall in a particular scale. So, we have to understand why some materials are highly conducting, some others not so conducting, others are insulators, and another group of materials are highly conducting, in the sense superconducting. So, there is a need to understand what is the basic mechanism of conduction, why different materials behave in a different way. And so, there are various theories from the very beginning of the understanding of the electrical behavior. People have put forward different theories. Not all theories are acceptable at this stage, but we like to discuss some of the history behind it, how exactly it got developed, some of the current understanding has been developed, and what are the basic concepts in that. So, these are the 3 different models or theories have been dealt with to understand the phenomena of electrical conduction. First 2 are particularly for metals, because metal was highly at that during those days when these theories were being developed, metal was one of the best conducting material, and their temperature dependence was of one kind, whereas the others have a different kind of temperature dependence of conductivity. So, people started discussing or understanding basically the conductivity behavior of metals to start with. So, the first theory which has been put forward is ideal gas model for metals, and then came the free Lagrangian, almost in a chronological manner. It is not that all of them came simultaneously, but it came in a chronological manner. first the ideal gas model of metals, then it was not really quite sufficient to explain all the properties. Then came the free electron theory of metals, that also had some limitations, and then finally the current model is more or less applicable to most of these materials are band theory of solids. So, we will discuss one by one. And what are the different assumptions. So, let us first take it up the ideal gas model to explain the conduction behavior of metals in particular, because most of the theories have been developed with metals, then semiconductors, and once we understand the basic phenomena or the basic concept, it will be applicable to ceramic materials as well, and it will be easier for us to understand what really happens in case of ceramics. In case of metals, it is outermost orbital electrons which form an electron cloud, that is known from the principle of chemical bonding, metallic bond. When we are talking about metallic bond, it is the you have the electron cloud, okay, the electron cloud, or sometimes it is called the Fermi gas around the positively charged atomic core, and are relatively free to move under an applied electric field. Inner electrons are tightly bound to the ion cores and therefore do not take part in the conduction process. I think that is a basic assumption. Not only the assumption, it is a true experimentally verified also, that only the outermost electrons take part in the both in the bonding chemical bonding mechanism, metallic bonds, as well as those are the electrons which take part in the conduction process. So, when we apply an electric field, actually those are the electrons which gets affected, whereas the inner electrons really remains unperturbed. The other assumption is the electron cloud is treated as an ideal inert gas, that is why it is called the ideal gas model. So, we are talking about a cloud, that means a electron gas, that is why it is also called the gas. So, it is as if a gas is there where the particles are basically electrons. So, it is very difficult to distinguish one gas from one electron from the other, but it is a combined effect of all the electrons put together, and the energy of the individual electrons depend on the temperature and applied field. So, when we apply an electric field, the energy changes, the kinetic energy changes, and also when you increase the temperature or change the temperature, the kinetic energy changes. So, it is assumed to be a gas, and so many of the basic concepts of gas dynamics or the molecular movement of the gas is applicable here. That is what the assumption is. In the absence of electric field, electrons move with randomly distributed thermal velocities. However, in presence of the field, they acquire a net drift velocity in the direction opposite to the field, because these are electrons negatively charged. So, they will move in the opposite direction. Now, the basic idea is, as the name suggests or the title suggests, that it is as if we have a gas, ideal gas, and whatever the concept of theories of molecular movement in gas, they may be applied here, and that is why it has been assumed as a ideal gas, and one has tried to explain how this movement can take place under the influence of an electric field. Well, this is a pictorial view of what can be happening, what is happening there, provided we assume that it is a gas. So, in case of this is just a conductor where you have ion cores, the positive ion cores, and the dots are electrons. So, these are the moving species. The ion cores are fixed at their own site, only the electron cloud which is moving or getting distorted under the application of the electric field. So, if you look at the particular electron, they are moving in a random fashion, that is the path taking followed by the electrons. Because of the thermal energy, there is always a movement of the gas molecules as also the electrons here. So, there is a random motion, they are moving, but there is no net movement spatial distribution so far as the volume of the solid is concerned. So, they may be moving in a random fashion, but the net movement is not there. Okay. So, that is because of the thermal energy they are moving, but if you have a electric field, then this random motion is to some extent gets order, although the random motion is not completely avoided because of the thermal energy. So, there will be movement of this nature, some kind of this nature, and there is a drift velocity. So, with the application of the electric field, with some time this electron has actually moved to this distance, but it has not gone through a linear distance, but straight line manner, it has gone through a zigzag manner. So, it is moving a much larger distance than actually we are observing from the outside. So, this there are 2 electrons has been given here. So, this is the kind of random motion which the gas molecules also have, and here it has been assumed for the electrons as well. Now, the velocity of a charge carrier, in this case electron, increases in the presence of an external field. This incremental velocity is normally termed as the drift velocity. That means, that is the net velocity in addition to its random motion, there is a net movement of the electrons in the particular direction depending on the application of the direction of the application of the field. So, during their movement the charge carriers normally collide. So, there is a random, because of the random motion, there is a possibility of the collision between the electrons, also with the different kind of other barriers or obstacles, and that results in the loss of drift velocity. So, once the collision is there, they come to a standstill, and however, after some time it again regain its velocity and goes to a higher value. Once again there is a possibility of collision, and then this is the way it goes on. So, the velocity of these electrons are actually not constant, it goes through a kind of sawtooth profile, and this is what one can expect. It goes to a very high value, suddenly there is a collision on the top and then comes back, and this shows the collisions takes place. So, that is the reason sometimes the drift velocity has been defined as the average velocity between the 2 consecutive collisions. So, there are a large number of collisions taking place either with the electron themselves or with the ion core. Okay. So, it is a moving where the ion core is also there, the positively charged ion cores. So, this is how it happens. Now, we have introduced a term called drift velocity. So, while the intrinsic velocity of a free electron is very high because of the thermal vibration, thermal motion, their drift velocity is quite low due to the chaotic motion, that is the random motion or the chaotic motion, and the collision of course. It is the collision which hinders their movement, and the average velocity is much lower, and so there is a order of magnitude calculation here. One can go through it. Once again the definition of current density. So, the Vd is J by N is equal to 10 to the power around the Avogadro's number, and then it becomes 10 to the 29 meter cube, and this is the electronic charge. So, assuming I about 1.6 amp per meter, there are 2 amps, one is extra, and I change this. Right. One 1.6 has been just used or be taken because this value is 1.6, so that you can get an regular figure. It can be any in that scale. Area is 1 meter square. So, by this one can get that Vd, the drift velocity, becomes about 10 to the power minus 4 meter per second, 10 to the minus 4 meter per second. This is much less than another term we will come across, that is the velocity, that is the root mean square velocity. Any kinetic energy term, thermal, because of the thermal vibration there is a velocity, and that velocity, the root mean square velocity, is about 10 to the minus 4 minus 5 meter per second. So, which is much higher. Okay. So, whatever thermal velocity what can acquire because of thermal vibration or thermal energy is much larger compared to the net velocity because of the applied electric field. So, its movement is much smaller, or the velocity is much slower. Well, this is what I was talking about, the RMS velocity. The ideal gas model for in an ideal gas, for an ideal gas the velocity depends on the temperature that I have mentioned. So, the kinetic energy is can be written as half me v square. V is the velocity because of the thermal energy, and then this is the temperature term 3/2 kT. Okay. So, this is an expression for the effect of temperature on the velocity of the gas molecules. The same thing has been written here for the electrons. Me is the electronic mass. So, from this actually Vrms is nothing but root 3 kT by me, and this is approximately 10 to the power 6 meter per second, which has been written there as 10 to the power 5, but in that order. Okay. At room temperature, so taking T equal to 300 K, so this becomes the Vrms, as sigma is proportional to Vrms, that is one kind of velocity of course, and sigma becomes also proportional to root T. However, the experimental observation is sigma equal to is proportional to 1 by T. The resistance actually increases, resistance increases with temperature, that has been the observation. So, from the ideal gas model one expects that the sigma is proportional to root T, okay, whereas the observation is just opposite, and that is the limitations of this, and that is the problem with this model. So, this cannot really explain the temperature dependence of the conductivity in metals. So, although one talks about a Fermi gas, but this gas is completely different than the normal inert gas molecules. So, that is one observation, and just to show that ideal gas model is not really suitable or applicable for to explain the temperature dependence of conductivity, electrical conductivity. This was the experimental parameter I was just mentioning, that the resistivity here of course not the conductivity, resistivity has been plotted as a function of temperature, the degree Kelvin, and if you talk about pure copper, which is one of the good conductors, one can see the resistance is increasing as a function of temperature, and it is almost linear relationship, slightly above slightly above 0 degree Kelvin, very close to or 100 degree Kelvin. This is not exactly linear, there is slight deviation from linearity, and although it shows that it goes to 0 at absolute 0, the resistivity should be absolute 0, but it is not. Once we discuss about the superconductivity, you will find there is always a residual resistance, it is not 0. So, only in very few elements or compounds we have seen that the conductivity really goes to 0, and those have been classified as superconductors, but metals do not, resistivity or resistance of the metals really do not go to the 0 at absolute 0. There is always some amount of residual resistance, but the more important for us for the time being is the temperature dependence. The temperature dependence is the resistance increases or the conductivity decreases as we increase the temperature. Now, there are some more data here, we will discuss that later. This is the effect of impurity atoms. This is pure copper. If we add some amount of nickel, either 2% nickel or 3% nickel, over and above the temperature effect, there is an effect of impurity as well. So, in fact, that is a common phenomena for almost all metals, that whenever you add some impurity to the system or to the pure material, its resistivity increases in addition to the temperature effect. So, that is what has been given here. This is the impurity, what we call the impurity scattering. We will come to that later. So, having discussed that ideal gas model, next theory or the next concept which has been put forward to explain the temperature dependence of conductivity or electrical conductivity of different metals are the free electron theory. There are of course two ways of looking at it: classical model of free electron theory and quantum mechanical concept of free electron theory, but we will discuss them more or less in a combined fashion. The basic assumption here that the electrons, once again the electrons are the free electrons or the outermost orbit electrons, those are the electrons taking part in the conduction process, are assumed, but they assume to have a constant but negative potential throughout the volume of the solid. So, we are talking about not just the thermal energy, but there is an electrical potential because there are charged particles, the electrons are charged particles and also moving in an environment of positive charges of the ion cores or the nucleus of each of the atoms. So, it is just not thermal energy only, but it is also the electrical potential which is of concern, and that was introduced later after the gas molecule ideal gas model failed. However, the potential is very high at the edges of the solid, and therefore, the free electrons are normally bound within the volume of the solid. Now, this is a kind of potential barrier one had assumed. If this is the total volume of the solid, there are free electrons which are moving in the solid within the volume of the solid, but it is not going out, it is not leaving the solid. So, therefore, it is assumed that there is a very high energy barrier. So, there is a high potential energy barrier, and this is actually a negative potential, but flat potential. So, throughout the solid, throughout the volume of the solid, it has a constant potential. That is one of the basic assumptions of the free electron theory. And so, the electrons within is a kind of a well, energy well, in which the electrons are moving in this, but it is not able to go out of the system, which is obvious. The electrons are really within the solid, and that is why assuming that this kind of a potential model has been considered. So, the kinetic energy of the electron is much less than that of the bound electrons. The kinetic energy of the free electrons is much less than that of the bound electrons. That is another assumption which has been made here. Well, the other most important aspect of the free electron theory, this is for the first time actually the electrons have been considered as have both characters, the so called the particle character and the wave character. That was the concept of the wave mechanical or the quantum mechanical approach, and the electrons are considered to have both particle and wave characteristics as per the de Broglie hypothesis, and the relationship between them, since they have a wave characteristics, they have a wavelength which is taken as a lambda, and then that lambda is related to the Planck's constant h as well as the mass of the electron, also the velocity with which it is moving. So, h is the de Broglie wavelength and h is the Planck's constant, m is the mass of the electron, and v is the velocity of the electron, free electron. So, if we have that, so one can consider a wave nature of the electrons. It is no longer a particle, or it has both the particle characteristics and the wave characteristics, and that is the relationship between them. So, when we are talking about particle, it has a mass, and when we are talking about a wave, it has a wavelength. Under this condition, we can, without going to the details of the calculation, one can find out what will be the energy of the free electron if we introduce this de Broglie concept and the best, and also we have a constant potential in which it is moving, and it is a energy barrier at the end of the solid in which it is there. So, based on the classical mechanics, the kinetic theory for a free electron may be expressed as E equal to, that is the energy of each electron is about half mv square, the kinetic energy, and V replace V by the de Broglie expression. So, you will get h square k square 8 pi square m. Okay. Now, k is another term which has been introduced here in addition to h. H is the Planck's constant, of course. K is a vector, and it is the magnitude of that vector is 2 pi by lambda. Once again, lambda is the de Broglie wavelength. So, the lambda equal to 2 pi by k. So, this is a vector which is called a wave vector, and that is defined by this. So, the wavelength, inverse of the wavelength actually, it is the inverse of the wavelength multiplied by 2 pi, or in other words the lambda is 2 pi by k. So, one can get lambda equal to h by mv, and therefore, velocity with which the electron can move is h by m lambda. Okay. So, once again the lambda is the wavelength and m is the mass of the electron. So, you have h k by 2 pi m, okay, replacing lambda by this. So, we get the velocity, and the kinetic energy is like this, and in fact ultimately if you replace V, although this expression has already been given initially, but this is how one gets it. So, the expression of the energy is we are not talking about the velocity now, velocity terms has been replaced, and we have a k term, okay, So, k is the, as I mentioned, it is a wave vector and it is the reciprocal of the wavelength, and this is a energy equation which has been plotted with respect to k vector, and this is a parabolic equation. E is a parabolic function of k. Okay. Now, this is the energy of the free electrons, energy of the free, not all the electrons, but only the free electrons, and it has, as k increases, the energy also increases. Now, this k can be related to the position, particular position of the electron within the solid. It is actually related to the reciprocal lattice space of the crystal, and it is related to that kind of a position of the particular electron within the volume of this volume of the material. So, at different places, what it basically means, at different places or different crystallographic positions or crystal lattice sites, the electron, whenever it is residing there, at different energy levels. Okay. So, and that will determine at what velocity they will move and what will be its mobility and so on. So, this is the E k curve, which is one of the most important findings of this free electron theory, and this explains many of the properties of the metals as well as many other solids. Now, these are, although this is supposed to be a continuous curve as a function of k, E is proportional to k square. So, it is a parabolic function, but this curve is really not a continuous curve. It is it is a quasi, one can call a quasi continuous curve. It is a discrete curves, and the discrete energy levels are as per Pauli explosion principle. We have plus half minus half spins, and they have slightly different energy levels. So, each of these electrons, depending on their quantum mechanical numbers, you have discrete energy levels, they are not a continuous energy line. Okay. So, that is another important aspect of this curve, the E k curve. Now, with this concept, we also introduce another important energy term, which is called Fermi energy. Okay. Now, the E k curve represents the discrete energy levels available in a solid. However, all of them may not be occupied by the electrons, only the lower levels are occupied depending on the availability of the free electrons. So, in a solid, theoretically you can have many such levels, energy levels possible energy states, and all of them need not be occupied by the electrons, and that how many of them will be occupied by the electrons, it depends on the availability of the total electrons, depending on the total number of free electrons available in that system. That also depends on the valency of that particular element. Some of them are monovalent, some of them are bivalent, some of them are trivalent. So, if monovalent metal is there, you will release the number of electrons will be less, whereas a bivalent metal, a divalent metal, more number of electrons in the same volume it will be available, and so on and so forth. So, depending on the availability of the free electrons, the outermost orbit electrons, the electron availability will be different, but the theoretical curve which has been computed is still valid. Okay. So, if you depending on the number of the available electrons, the lowermost energy levels will be first occupied, and the rest of the energy levels, although they exist, they theoretically they can have the electrons can have this kind of energy levels, but there will be no electrons to occupy them. So, it is the occupational situation, that means the filling up of the energy levels will be from the lower level, and more depending on the more and more energy levels available, the more and more electrons available, more and more energy states will be occupied. So, in this context, Fermi energy is defined as the maximum energy up to which all the energy levels are occupied by the free electrons at a temperature of absolute 0. So, Fermi level, of course, these energy levels will be there, but the occupancy will change with temperature, that we will see in a few minutes or after some time. So, but what we are defining a particular energy level, Fermi energy level, is only for absolute 0. So, at absolute 0, whatever the maximum energy level up to which the electronic states or the energy states will be filled up by the electrons, that is what we call the Fermi energy, and it has once again a very important connotation, as we will see later. So, this is in this diagram, this is the Fermi level or EF, and below which all these energy level, all the energy states available are actually filled up. Although one thing we must also remember, or I must point out, this is a 2-dimensional curve, this is a 2-dimensional plot, but actually this is a 3-dimensional figure. Okay, it is a 3-dimensional figure in both x and y z directions. It is available, it is a volume. So, it is actually a paraboloid. Okay. So, it is actually a paraboloid. So, it is not a line, actually it is a surface, So, it is like a container. So, in which as we put more and more electrons, lower states are getting filled up, and it has been as if the container has been filled up with water up to certain level. So, the highest level up to which the container has been filled up is actually called the Fermi energy, and that is at absolute 0. However, we will see afterwards that this energy is a kind of constant, and at higher temperatures the occupancy changes, but the energy level remains same, and at that time we will see another way to define this particular energy is the occupancy level will correspond to about 50% occupancy. So, at temperatures other than 0, the Fermi energy corresponds to 50% occupancy, and that we will see later. Some electrons will jump to the higher, and there will be some vacancy. But the occupancy level will not be 100%, it will be up to 50%. So, but the EF, the energy level, is a constant for a particular system. So, with this we come to the end of this particular lecture. We will continue this discussion on the electrical phenomena in ceramics or in metals in solids in general in our next class. Thank you for your attention.